Here are a couple of orthogonal river problems. First question, which one's probably harder for most students? Well, whichever one is asking you to solve for a component vector, I feel like is harder because it's natural to add up two vectors to get a resultant, and it's less natural to subtract one component from a resultant to get the other component, or at least less natural. So this first one's going to be the more straightforward kind because we're finding actual velocity, and that's going to be the sum of two component vectors, which are the heading and the speed in still water. Those kind of go together, and then the river's current. And then this other one is finding speed and heading. So I want to try to do these in the same manner as a non-orthogonal problem, which means I'm going to draw a little table to do these. Let me, guess I better write some stuff down while I do this. Let me see if I can split my screen here. I'm not doing very well. Okay, so first, I'm going to make a table. These are the x components and y components of the vectors. I'm not even doing a drawing right now. I'm going to add up my, we'll make this a really big thing. These are the component vectors, and then this is going to be the resultant vector. So one of the component vectors is the speed and heading of the kayaker. So I'll draw off on the side. The speed and heading is eastward. So here's north, south, east, west, and the speed in still water is 4.5 meters per second. So this represents the heading and speed in still water. So I'm going to put that here, heading and speed in still water, which is a component, and it's all the way I've drawn it in the x dimension. So x is 4.5 meters per second, and there is no y component to this, so that's just 0. Now the other component vector is the river's current, and it says it's a southward flowing river. So here's the river's current. It's going south, and that's at a rate of 2.5 meters per second. So the current, it's got a y component but no x. So y is negative 2.5 and x is 0. So if we were doing an orthogonal or non-orthogonal problem, we'd have an x and a y component because it's not straight up and down, it's not straight left and right. We wouldn't have these zeros. It just looks a little funny because I'm creating the table, and we don't usually do that here. So the resultant is the actual velocity of the kayaker, and that means relative to the Earth. So that's just the sum of these other two. 4.5 plus 0 is 4.5, and 0 minus 2.5 is negative 2.5. So I can visualize now the kayaker's actual velocity. Let me switch to this screen, make it bigger. If I draw this on a map view, first I'll think of this as the y dimension and the x dimension. So the x component of this is 4.5, positive 4.5. The y component's negative 2.5. I'll draw these two vectors head to tail. And then that means the resultant, the vector that we get if we add these two components together, the actual velocity or the speed of the kayaker is this long. If this is 4.5 and this is 2.5, this would be the length of the speed, and then this direction right here, which I'll use this angle theta to describe, I can find out. So to get this, it's just the hypotenuse, which is going to be the square root of 4.5 squared plus 2.5 squared. Hopefully no untoward things will pop up on my phone. Now I have to take the square root, 5.15-ish. So that is the speed. Now the direction is like this. And if this is east and this is south, and I'm going to find it convenient to find this angle right here. This is going to be some angle south of east. So you start out saying, here this is an eastward direction. I'm going to swing this far to the south of that. Yes. And the distance to the south is dictated by the angle. That's how I'm going to describe direction. So I need that angle. So I can say that I'm going to write this differently. This is 4.5. This is 2.5. This is the opposite. This is the adjacent leg. So sine of theta equals 2.5 over 4.5. Therefore, the inverse sine of 2.5 over 4.5 gives me theta. So 2.5 divided by 4.5 is that. And then I go to second, inverse sine, 33.7 degrees. And I don't want to stop there. I want to say it's 33.7 degrees south of east. Now if you had found this angle, I'll just call that alpha. Alpha would be this minus 90, or 90 minus this. This would be a 56 degree angle. So I could also call this 56 degrees east of south. Because if I start out thinking about this direction, that's south, and then I swing this way 56 degrees, that gets me to where we're going. So there. So that's one way to do this. I guess I could show you the other way, which is where you just draw this out. So this is a component vector, this is a component vector. I draw 4.5. This is the heading and speed in still water. And then I add to that the river current, 2.5, and then this is the resultant. And it seems very similar to what I've got here. The only difference is I've very carefully, meticulously separated each of these vectors into their x and y components. Let me do the other one. This is the one I consider to be a little bit harder. And the reason is because we're looking for a component, and that usually throws people off. So now I have speed and heading of a kayaker. So I'm going to just draw my table first. Here's my x, y. These are the component vectors. They have to add up to the resultant vector. The resultant vector is always going to be the actual velocity relative to the Earth of whatever is in the current. In this case, the kayaker is in the current. The component vectors are going to be the current and the heading and speed in still water of that thing. So heading and speed in still water. So these two are going to add up to that. These two x components are going to add up to this x. These two y components are going to add up to that. This is an orthogonal problem, so again, this is easy. So I'm reading the problem, looking for speed and heading. So I'm not going to have these. These are what I'm trying to find. The river has a 3.8 meter per second westward current. So it would look like this. This is my map. The current is 3.8 meters per second to the west. So that has a negative 3.8 x component, but no y. Zero. And this we're not going to know. We're going to get the actual velocity. The kayaker's velocity is 6.2 meters per second southward. So this is the actual v, and this is 6.2 meters per second. So in the y dimension, this is negative. There's no x component, so I have 0, negative 6.2. So what I'm looking for are these. And since these two components, current plus heading and speed in still water, gives me the total, I could take the total, subtract one component, and that gives me the other one. So this is going to be 0 minus negative 3.8, which gives me 3.8. Which makes sense, because if you're going to have a total x velocity of 0 and the current x velocity is negative 3.8, you've got to have a heading and speed in still water to cancel that out, so you're not moving in the x direction. And then here, for y, it's going to be the total, negative 6.2, minus this, 0, which is negative 6.2. And that should make sense also, because if the total is total y velocity is negative 6.2, and the current has no y component, the entire y component has to come from the heading and speed in still water. So here's my answer. I just need to convert this to a speed, which not just, this is the speed in the x dimension, this is the speed, or at least velocity in the y dimension. I need to get a speed, a total speed, and then I need to get a direction. So x, I'll do y first this time. I drew this vector, drew the x vector first last time. I'm going to draw the y vector first, just to show you can. So here's my y. Going down, because this is negative, and that should be 6.2. And then the x component is positive 3.8. Add this on head to tail. So there they are. Those are the two component vectors. I'm going to assemble them into the resultant. So this is the actual way the kayaker is heading and how fast, at least compared to those two things. So I'm going to find this angle, and I also need the length of this. The length of this is just the square root, 6.2 squared plus 3.8 squared. Get rid of that. And then square root, I'll call it 7.3. Oh, what the heck, 7.27. That's the paddler's speed in still water. And then the direction, oh, you know what I did earlier? Oh no. On this previous problem, it just occurred to me, I used sine, inverse sine, and I should have used inverse tangent. Let me fix this first. So this, actually, you know what? I'll fix that in a minute. Try to move on. But so this is the opposite. This is the adjacent, and that should be tangent. Tangent theta equals 3.8 over 6.2. Therefore, the inverse tangent of 3.8 over 6.2 equals theta. So second tangent, 31.5. So this would be 31.5 degrees east of south. All right, let me go back and fix this. This should say tangent also, because I'm using this. This is the opposite. This is the adjacent, and tangent is opposite over adjacent. So therefore, the inverse tangent, not sine, 2.5 over 4.5 gives me the answer. (29 degrees). South of east. And if I do 90 minus that, it's going to be 61 degrees east of south. And instead of 31.5, if I subtract that from 90, I get 58.5 degrees south of east. Make sure that's right. Yeah.